Hi, this is an example problem from Chapter 13 on heat conduction. Pause for a moment and read the question. All right, so we've got a situation here where we have heat conduction through a copper and aluminum rod, equal diameters, and let's recall heat conduction when we have a situation with a hot reservoir at a temperature T hot, a cold reservoir maintained at temperature T cold, and if you have a rod that's connected between the two, heat will transfer continuously from the hot to the cold at a constant rate of heat flow. And this is the equation that describes it. Let's go ahead and write that down. And in our problem, we've got two rods that are connected somewhere in the middle. So we'll go ahead and draw a picture of that. So the equation is Q, the heat transfer during conduction, equal to K, the constant for thermal conductivity, multiplied by delta capital T times A divided by L times little delta T. Now we want to remember the difference between the capital T is for temperature, little t is for time. This is the total heat Q that is transferred through conduction in a certain amount of time, delta T. But we can also, a lot of times, we divide both sides by little delta T. Then what we get is the heat per unit time, the heat flow rate through conduction. And I'm going to rewrite this like the thermal conductivity times the cross-sectional area of the rod divided by the length of the rod. And delta T, in this case, delta usually means final minus initial, but in this case, it always means T hot minus T cold. All right, now for our particular situation, let's go ahead and draw a picture of what we have here. We have a aluminum rod and a copper rod that are connected between two temperature reservoirs. All right, so here we've got a picture of the reservoir that's hot at 100 degrees Celsius, contacted with the copper rod, which goes down to 40 degrees, connects with the aluminum, and then connects the aluminum rod with the cold reservoir at 0 degrees Celsius. We are told that the length of the copper is 0.15 meters, and we're asked to solve for the length of the aluminum. Now for this problem, we're going to use the form of the equation that says Q divided by the time interval, the heat rate. And we've got two different objects, copper and aluminum. Of course, the heat that flows through the copper, it's got to pass through the copper, then the aluminum to get to the cold reservoir. It turns out that in this type of process, since the temperatures are fixed, the heat flow is going to flow right through the copper rod, through the aluminum rod, and as the hint tells us, none of the heat is going to accumulate in the copper or the aluminum. Otherwise, the temperatures would change. They wouldn't remain static as they are. Therefore, the heat flow through the copper and the aluminum has to be equal, and we can write this. Q delta T for the copper is equal to the heat flow, Q delta T, for the aluminum. And we're going to go ahead and substitute in the various variables using the equation. So we've got the specific heat of the copper, sorry, not specific heat, thermal conductivity of the copper times the area of the copper tube divided by the length of the copper tube, and that's all multiplied by delta T, hot minus cold, for the copper. And then we've got the same thing on the other side for the aluminum. So thermal conductivity of aluminum, the area of the aluminum rod, the length of the aluminum rod, which we're trying to solve for, and the temperature difference between the hot and cold end of the aluminum rods. So let's see if we can kind of figure out some of these things here. So for copper, maybe here. For aluminum, here. What do we know about the thermal conductivities? Well, we have to go ahead and look those up. So let's go ahead and do that. So for copper, we've got 390, and notice the units are joules per second meter degree Celsius. For aluminum, we've got 240. All right. Now the cross-sectional area, that's the little section of the pipe there. We're told these have the same diameters, so we know that whatever the copper cross-sectional area is, it's going to be the same as the aluminum, which is good because in the equation over here, we can go ahead and just divide them out. If they're equal, we can divide by the same number on both sides and it cancels, right? Let's see what the temperature changes are for these. So for copper, delta T copper, remember that's T hot minus T cold. The hot side of copper is 100 degrees Celsius. The cold side of copper is 40 degrees where it touches the aluminum. So this delta T for the copper is going to be equal to 60 degrees. For the aluminum, we've got 40 degrees Celsius minus 0 degrees Celsius, or in other words, delta T aluminum is just equal to 40 degrees Celsius. T hot minus T cold for the aluminum. And with that, I think that we have everything we need to know here. We've got the temperature changes, hot minus cold for each. We've got the thermal conductivities, and we also know what the length of the copper is. We just need to solve for the length of the aluminum, which means doing a little bit of algebra here. So let me go ahead and let's see. Let's multiply both sides by the length of the aluminum here. Cancel those out, and on the other side, we're going to be multiplying by the length of the aluminum, and we'll have it over here. And we've still got KCU delta T CU over L CU, which is equal to KAL times delta T AL. Now we're going to take the reciprocal of this whole term here and multiply by both sides to cancel it out. So if I multiply on this side, I'll be left with just length of the aluminum. On the other side, I'm going to multiply by the reciprocal of this. So we start out with K aluminum, delta T aluminum, and the reciprocal of that is L for the copper divided by K for the copper times delta T for the copper. And in fact, let's go ahead and just rearrange this a little bit. So this is L for the copper, and I'm going to do a ratio of the two thermal conductivity constants and a ratio of the temperature changes. And why did I do the ratio? Well, since they have the same units in the ratio, all I need to do is go ahead and plug in the numbers, and the units are the same, so they're going to cancel. So here we have the length of the copper, which is given as, here it is, 0.15 meters. And then we're going to take the aluminum divided by the copper thermal conductivity, so aluminum 240. I can ignore the units again because they're going to cancel. And of course, notice that the units are Celsius, right? So we are having degrees in Celsius, which is proper for that. And the delta T aluminum divided by delta T copper, aluminum, it's 40. Again, I can ignore the units because it's the same. They cancel. And for the copper, it's 60. And so basically what we need to do is just calculate this number, put that into our calculator, and we'll solve for the length of the aluminum rod. It turns out that it's going to be equal to 0.06 meters. All right. Now, since the aluminum